Okay, so now we're into KW, pH, and pOH, which is actually just a review from grade 11. So it's nothing new. What we're going to be doing right now is just reviewing some of the concepts from Chem 20 in terms of acids and bases, because next week and the week after, we're building on those and we're going to be learning a little bit more, okay? So this shouldn't be new. It should be review. Even if it's a bit hard, it should be information that you already know. So example 1, guys, says you have a 2.50 times 10 to the negative 3 solution of nitric acid. And it says it's a strong acid. And that's because it's in the top 6 of your data booklet. What do I mean by that? If you remember last year, I told you guys in your data booklets on page 8 and 9, the first 6 acids are all strong acids, okay? What does that mean? Strong acid just means, guys, that it ionizes completely, okay? Then it says calculate hydronium concentration, hydroxide concentration, pH, and pOH. All right. The first thing that we should start with, guys, is the hydronium ion concentration. Why is that? Well, if we have an acid, that means that the acid is going to ionize to produce hydronium. So nitric acid, guys, its chemical formula is HNO3, and it's aqueous because it's in water. And because it's in water, it reacts with water. Because it is a strong acid, we draw a single arrow, put 100% above, and it's going to produce hydronium, okay? Now, that means that this hydrogen went from HNO3 over to water. It lost the hydrogen, which means the remaining ion is NO3 minus, okay? Now, all of you ladies and gentlemen know the molar coaster. You know that I love it and that I preach it, okay? If you look at the question, it didn't give us the concentration of hydronium, okay? It gave us the concentration of HNO3. Now, if I just write that underneath, 2.50 times 10 to the negative 3 moles per liter, okay? I'm going to write that's the concentration of nitric acid. If you know that you have a single arrow, you can always ride the molar coaster. You divide by where you start, 1, multiply by where you're going, 1, and you're going to recognize that the concentration of hydronium is going to be the same. There's a 1-to-1 relationship. Okay, and conceptually that makes sense, because if you have this much acid and it reacts completely, you will have this much hydronium. So we've already solved the first part of this question, which is what's the concentration of hydronium? Well, the concentration of hydronium is just the same. Okay, good. So we're done now. Step 1, done. Okay, now we need to figure out what the concentration of hydroxide is, what the pH is, and what the pOH is. Let's just go with pH. Okay, so we're done hydroxide or hydronium. Let's just go to pH. We know there's a super easy to use formula, and that formula is pH is equal to negative log concentration of hydronium. All right, you guys remember that from last year. So I'm just going to put in negative log bracket 2.50 times 10 to the negative 3 moles per liter. Get my handy dandy calculator out because it's a challenging calculation to do in my head. So I'm going to do negative log like that, bracket 2.5 times 10 to the negative 3 close bracket, and I'm going to get 2.6020 ... no units. Okay, pH does not have units. However, pH has weird sig digs. The number of sig digs in the concentration, okay, number of sig digs in concentration is equal to the number of decimals in the pH. So there's 3 sig digs, 3 decimals in pH, 2.602. Okay. Now, 2.602, is that number 7, below 7, or above 7? Okay, it's below. And if it's below, it means it's an acid, which makes sense because we have nitric acid. So far, it's all making sense to us, okay? Now, the third thing that we can do, guys, is we can calculate the concentration of hydroxide. Well, how can I do that? I have pH. I just introduced to you guys the following formula. For any solution, the concentration of hydronium times the concentration of hydroxide is equal to Kw. Kw is a constant. It doesn't change. It will always be the same. So I can rearrange this formula, divide both sides by hydronium, and end up with this. Okay. So I can find the concentration of hydroxide because I know this and I know that. So I'm going to do 1.00 times 10 to the negative 14 divided by 2.50 times 10 to the negative 3. Units are a little weird here, okay? We know the concentration has moles per liter. So we're just going to assume that the concentration moles per liter stays, or units, sorry. So in my calculator, I'm going to do bracket 1.00 exponent minus 14 divided by bracket 2.50 exponent minus 3. And I'm going to get, guys, 4.00 times 10 to the negative 12 moles per liter is the concentration of hydroxide, sorry. Okay. Now, let's see if this makes sense to us. If we have an acid, we have a lot of hydronium, not a lot of hydroxide. Okay. Is this number bigger than this number? Yes. This is exponent negative 3. This is exponent negative 12. So we have more of this than hydroxide. So we have an acid. Now, my last thing that I have to do is calculate pOH. Because I have the concentration of hydroxide, I could do pOH equals negative log concentration of hydroxide. I could do that easy peasy. But what I'm going to show you guys is something we learned last year. We learned that the pOH plus the pH is always going to be equal to 14. They are opposite scales, okay? If I have pH, which I do have, I can easily find the pOH by just subtracting it. It's a really, really easy calculation. So my pOH, guys, is 14 minus 2.602, 11.398. Okay? And we're done.